So in this session on signals and systems, we are going to define what an IIR filter is, study couple of its properties, and then compare it with the performance of the FIR filters. That is what we are going to do. The implementation of the IIR we will study in the next session. All right, so let us start. Let us start by defining the input-output equations for FIR as well as IIR. FIR we have already studied. For FIR filter, the output is given by this equation, and you can see that output depends on the current value of the input and some of the past values. So xn minus 1 is a past value 1 sample time earlier. This is a past value 2 sample times earlier, and so on. And once you know B0, B1, B2, effectively you have designed the filter. And so far we have studied how to do it analytically, and also we have studied a MATLAB function for this. All right. Let us now define the input-output equation for the IIR filter, that is the infinite impulse response filter. So here the output depends on the current value of the input, some of the past values of the input. So far it is similar to the FIR filter, but then it has additional terms where the output also depends on some of the past values of the output. So these coefficients are written as minus A1, minus A2, and so on. So that is the difference between the difference equation for FIR filter and IIR filter. In FIR filter, the output does not depend on any of the past values, whereas for IIR filter, apart from the present value, some of the past values of the input, it also depends on some of the past values of the output. All right. So because these two equations are different, the couple of properties of these filters are different, and we will study them. So first thing we study is the impulse response. We have already studied that for FIR filter, the impulse response corresponds to the sequence of the coefficients themselves. So the impulse response would be B0, B1, B2, etc. And that is how we define the, we design the FIR filter. But now since the number of coefficients are necessarily finite, the impulse response is going to be finite for FIR filters. So these FIR filters are also called as non-recursive filters because output has no effect on the next outputs. So for that reason, they are also called as non-recursive filters. Recursive filters, where some of the past values of the output also decide the current value of the output. So they are also called as recursive filters. Now for IIR filter or recursive filter, even with finite number of coefficients, the duration of the impulse response is infinite. Okay, so this is quite different than FIR filter, where since the number of coefficients are necessarily finite, the impulse response is also finite. Now with IIR filters, even when the number of coefficients are finite, the duration of the impulse response is infinite. So let us show this by using a simple example. So this is a one of the very simple equations for an IIR filter or a recursive filter, where the output depends on the present value of the input. The B0 is equal to 1, and here it also depends only on one of the past values of the output. So A into Y n minus 1, one sample time earlier. All right. So using this equation, what we are going to do is to calculate the impulse response. All right. So impulse response means the output that you obtain, assuming that input is a unit impulse. So delta n. And digital unit impulse, as you know, is very simple. At n equal to 0, it has a value 1. And for all other values of n, it is 0. So considering this, let us calculate the output for various values of n and put them in a table. So suppose n is equal to 0. Then this is x0, which is delta 0. And as we know, unit impulse at n equal to 0 has a value 1. At this point, let us assume that the initial condition, so n is equal to 0, so y of minus 1, that is the initial condition for the output, and let's assume that this is 0. If this is 0, then the output is xn, which is 1, plus a into 0, which is 0, so the output is 1. Okay. Then next consider n equal to 1. When n is equal to 1, as we know from the definition of the digital unit impulse, xn is equal to 0. But now the previous value of y is 1. So a into 1, the current value of the output is a. When n is equal to 2, again this is 0, but then the output can be obtained by multiplying a with the previous value of output. So a into a, that is a squared, then a into a squared, that is a cube, and so on. So it continues without limit. So if you look at the sequence of values for the output, it will look like this: 1 followed by a, followed by a squared, followed by a cube, a4, etc. So in general, it's a raised to n. And the number of possible values that you will get are infinite. So you see that the duration of the impulse response for a recursive filter or an IIR filter is infinite. Although we have shown this for one particular example, it is quite generally true. Okay. Now, the fact that IIR filter has an impulse response which is infinite, it has got a couple of important points. So let us discuss them. What is the significance of this impulse response being infinite? Okay. So first of all, suppose you assume that mod of a, so a could be negative or positive, but suppose mod of a is greater than 1, then what will happen? If this is greater than 1, for example, this is 2, then this will be 2 raised to 4, then 2 raised to 3, 8, 2 raised to 4, 16. This goes on increasing, and it will increase without bound as time n increases. Therefore, this particular filter is not stable when mod of a is greater than 1. Now this is something which never happens with FIR, since the impulse response is of finite duration. So FIR filter is inherently stable. Of course, if mod of a is less than 1, then IIR filter also will be stable, because the output will not increase without bound. For example, if this is 0.5, then this will be 0.5 squared, 0.25, then this will be 0.5 cube. So this goes on decreasing as n increases. So it does not increase without bound, and therefore if mod of a is less than 1, then IIR filter is going to be stable. However, note that if you do not design the IIR filter properly, it could become unstable, whereas FIR filter is inherently stable. Okay. Let us study the other significance of the infinite impulse response, and that relates to the order of the filter. Now, the transfer function of the filter depends on the duration of the impulse response. Remember, the discrete time Fourier transform of the impulse response is the transfer function. So, larger the number of terms in the impulse response, higher will be the order of the filter, and therefore sharper will be the response. Okay. So as we said, so the order of the filter is higher, longer the impulse response, and magnitude response is sharper. Now for IIR filter with mod of a less than 1, the impulse response decays with time. Still it has a long duration before it becomes negligible. So filter is sharper even with less number of coefficients, because IIR has got very large number of samples even with less number of coefficients. But for FIR filter, the impulse response directly depends on the number of coefficients. So it will require a very large number of coefficients in order to get a sharp filter. So as we said, for FIR filter, you will need large number of coefficients to get large length of the impulse response. Alright. So these are the two significant points of the fact that impulse response of the FIR filter differs from the impulse response of the IIR filter. So there are 2 points. One regards stability. IIR filter could become unstable. FIR is inherently stable. But for the given order, the IIR filter in general will be sharper than the FIR filter. Okay. Let us now look at one more property which is different for FIR and IIR, and that is the phase response. Okay, we'll be able to show that for FIR filter the phase response is linear. It has a linear phase response, whereas IIR filters have non-linear phase response. So the applications of FIR are different and the applications of IIR are different. Remember, the advantage of the FIR filter is that it is inherently stable and it has a linear phase response. Whereas the advantage of the IIR filter is that even for small number of coefficients it has a sharp response, but the disadvantage is that it has a non-linear phase response. Okay, so what we are going to do now is to consider two specific difference equations, one for FIR, one for IIR, and show that for that particular difference equation the phase response is linear for FIR, and for the chosen equation for IIR we will show that it is non-linear phase response. And although we are doing it with simple example, it is generally true for all FIR filters and IIR filters. Alright. So let us first start with FIR. So let's say we have got a FIR filter with three coefficients, B0, B1, B0. In general, the FIR design is such that this is symmetric around the center value. So there are three coefficients. So the second coefficient is the center coefficient. The one to the left of that is B0 and one to the right of that is also B0. So we are assuming in this case that these coefficients are symmetric around the center value, and that is generally the case when you design the FIR filter. For example, if you had 5 coefficients, then you will have 1, 2, third coefficient will be the center value, then you will have 4 and 5. So first coefficient will be same as fifth coefficient and second will be same as the fourth coefficient. Anyway, let us consider this example which has 3 coefficients, which is symmetric around the center value. And now what we want to do? We want to find a phase response for this and show that it is linear. Alright. So as we said, typically the coefficients are symmetric around the center value. Now to find the transfer function, what we do is we take the DTFT of both sides. So to find the transfer function, we take the discrete time Fourier transform of both sides. So y omega. Now usually this is written as e raised to j omega, but for simplicity I have just written y omega. It does not matter. So y omega is equal to b naught DTFT of xn, that is x omega, and then from the delay theorem, the delay in the time domain corresponds to the phase shift in the frequency domain. So this is b1 into x omega into e raised to minus j omega, because the delay is 1, so the coefficient of omega is 1 in this case. And here b0 x omega into e raised to minus 2j omega, because the delay is 2 samples. Alright. So now we will manipulate this in order to show that in general, note that this is a complex quantity. So it will have magnitude as well as phase. And what we want to do is to manipulate this in order to show that phase is a linear function of frequency. Alright. So we find the transfer function by dividing both sides by x omega. So left hand side becomes y omega by x omega. That is the transfer function. Here x omega cancels. And now b0 is common to first term and the last term. So we take it out as common. So this is 1 plus e raised to minus 2j omega plus b1 into e raised to minus j omega. Now let us manipulate this a little. So what I have done, I have taken out e raised to minus j omega common. So b0 into e raised to minus j omega. So inside the bracket I will first get e raised to j omega and then plus e raised to minus j omega. This term is equivalent to this. You can easily note this. If you expand it, This is e raised to j omega into e raised to minus j omega. So that is e raised to 0, that is 1. And then e raised to minus j omega into e raised to minus j omega. So exponents add, so it becomes minus 2j omega. So that is how we have written. And plus b1 into e raised to minus j omega. Okay, so now e raised to minus j omega is common, and note that e raised to j theta plus e raised to minus j theta will be 2 cos theta. So this can be written in this form. E raised to minus j omega is taken common. So this multiplied by b naught becomes 2b0 cos omega, and this is b1. So e raised to minus j omega into b1 plus 2b0 cos omega. Now if you look at this bracketed term, it has only real values. So the phase of this transfer function is decided only by this part, and the phase clearly is e raised to theta. So in this case theta will be equal to minus omega. So theta is minus omega. So this tells you that for this specific example of the FIR filter, phase is indeed linearly related to omega. And if you recall, in one of our earlier lectures we had told that if we don't want the signal to be distorted, then magnitude response should be uniform within the band of interest, and phase should be linearly related to the frequency. So which is indeed the case for the FIR filter. Okay, now we will show that for IIR filter the phase is nonlinear, again by taking one simple example. So let us take this example, yn equal to xn plus a y of n minus 1. So for simplicity we have taken a very simple equation, but the result that we will get is generally true for IIR filters. So again taking dTFT of both sides, so we get y omega equal to x omega plus a into y omega e raised to minus j omega, again using the delay theorem. Then dividing both sides by x omega, we will get this. Okay, actually what you have to do is to bring this second term on this side. So this will be y omega into 1 minus a into e raised to minus j omega, and then you manipulate this and obtain the transfer function, which is 1 upon 1 minus a into e raised to minus j omega. So e raised to minus j omega can be written as cos omega minus j sin omega. So in that case the phase, since this is in the denominator, the numerator has a phase angle which is 0. So the net phase angle will be numerator angle which is 0 minus the denominator angle. That is why this minus sign here. And you can see in this case that when you expand this, this becomes 1 minus a cos omega plus a j sin omega. So the coefficient of the imaginary term is a sine of omega. So the theta is given by minus tangent inverse a sine omega divided by 1 minus a cos of omega. And this is clearly a non-linear relationship between theta and omega. So one disadvantage of the IIR filter that it has got a non-linear phase relationship with respect to omega. So wherever the linear phase relationship is required, wherever phase relationship is critical, you will use a FIR filter, and wherever it is not critical, you could use IIR filter, because for less number of coefficients you get a sharper response. Alright, therefore let us quickly look at the places where FIR filter is used. So where linear phase relationship is critical, like in audio signal processing, in image processing, in multi-rate systems. Okay, these are the areas of application of the FIR filters. Also where stability is important. For example, in adaptive filters, stability is important because you're using feedback. So therefore FIR filters have these applications because of their properties of being highly stable and linear phase relationship. But if the linear phase relationship is not critical and stability can be ensured for the IIR filter, then you will use the IIR filter. So low order for sharp cutoff. So in narrowband filters, wherever the linear phase relationship is not so much important, you will use a IIR filter. Also, in control systems, you often want fast response and nonlinear phase response can be tolerated, then IIR filter will be used. Also note that design of the IIR filters is quite involved, but then a lot of analog filter design theory is available. Most of the tables are available, and by using appropriate transformations, it is possible to design IIR filters from the analog prototypes which have been extensively studied historically. Whereas FIR filter design is separate, we have already studied that, but it does not follow analogously for the design for analog prototypes. So this is one academic advantage, you can say, that you can design the IIR filters from the analog prototypes. But in general, the IIR filter design is going to be involved. It becomes simplified only because it follows from the analog prototypes which are available. All right. So in this session, we have introduced the definition of the IIR filter. We have studied a couple of its properties and compared these properties with the FIR filters and the significance and the applications. In our next session, we will see how to implement the IIR filter. But that's all for now.